This slide's presentation will be your introduction to the concepts of sensitivity, specificity, receiver-operator characteristics curve, as well as likelihood ratios. I say introduction to because you will use these terms next year a whole bunch in orthopedics. It's really important to understand these terms in order to interpret any kind of special test that you're going to do in the future. To start off, let's look at a 2x2 contingency table. Kind of similar to what we saw when we were looking at risks versus odds. However, this time it's a little bit different. This 2x2 grid has on the top true diagnosis. That means the person really has this problem. Okay, and you can see underneath that it says DX is diagnosis positive and diagnosis negative. So the diagnosis positive are people who actually have the diagnosis in that column. The diagnosis negative are the people who don't have that diagnosis. So let's take any diagnosis. Let's just say shoulder impingement. Okay, just for the sake of having something to think about. If you have shoulder impingement, your diagnosis is positive. If you don't have shoulder impingement, your diagnosis is negative. How do you know if you really have shoulder impingement? Well, you could go ahead and have an MRI done, or you could try a special test. So oftentimes people create special tests in order to be able to identify a problem in the absence of an MRI or arthroscopic surgery or something like that. Right, so the special test that you would do for shoulder impingement could be something like empty can. Now, how do you know that the empty can test is any good at diagnosing shoulder impingement? Well, what you'd have to do is take a large sample of individuals, say 300 to 500 people or so, and some of these individuals have shoulder impingement and some of these individuals don't have shoulder impingement, and then you perform the empty can special test to see whether or not the results are positive, and then compare that to results that were gotten by via an MRI. Okay, looking on the side of the 2x2 table, you have the test result. If the empty can test was positive and you really had shoulder impingement, you would be considered a true positive, and that is in grid A. Empty can was positive, you have shoulder impingement, you would be one of the individuals in box A. Okay, let's say that empty can was positive, but you really didn't have the diagnosis. That means that you're a false positive, and you'd be categorized in little grid B. Now, let's say that the empty can test was negative, but you really did have the diagnosis of shoulder impingement. That would put you in little grid C, and you would be considered false negative. Okay, and if empty can test was negative, but you really didn't have the diagnosis of shoulder impingement, then that would be considered a true negative result, and you'd be classified in little box D. Understanding all this stuff, that where the true diagnosis comes from and the test result, that's important for being able to calculate the sensitivity and specificity of a test. So let's look at sensitivity. Here's the sensitivity of a test. The sensitivity of the test is the percentage of true positives that actually have the diagnosis of the problem in the total population. So this is kind of like risk, if you remember, only we're calculating columns here and not rows, right? So the total population that had the diagnosis of shoulder impingement is seen in the area that's highlighted in the fluorescent green. Okay, these include people who actually had the diagnosis and tested positive with empty can, as well as those who have the diagnosis and tested negative with empty can. So, to calculate the sensitivity of the test, you would take the number of individuals in box A, okay, and divide that by the number of individuals that actually had the diagnosis, and that would be box A plus box C. Okay, you should know that a highly sensitive test, let's say you have 100% sensitivity in your test, you won't miss a positive result. And that also means that if you have a very highly sensitive test, say 100% sensitivity, a negative test rules out that diagnosis. Okay, you can remember that by thinking SNAPT. Sensitivity, SN, and then negative, out. A highly sensitive test rules out the diagnosis because it's designed to not miss a true positive result. Conversely, you have the specificity of the test. In order to calculate the specificity of the test, you're looking at people who didn't have the diagnosis. Okay, a highly specific test is really, really good at finding true negative results. So, if the diagnosis is negative and the test, the empty can test is negative, then you're looking at little grid D there. That's the true negative. So in order to find the percentage of true negatives in the total diagnosis negative population, what you do is you take the number that resides in box D, okay, and you divide that by the total number of individuals in the diagnosis negative population, which would be box B plus box D. Okay, this will give you your specificity. Now you should know that, as I've said, a highly specific test will not miss a negative result, but you should also know that a highly specific test, if you get a positive test and your test has 100% specificity, then that person has the diagnosis because this test won't miss a true negative. Okay, how you remember that is spin. So SP is specificity, P is for positive, and N. So a highly specific test, if the test is positive, that rules in the diagnosis. That means that the person really has the problem because the test is designed not to miss a true negative. So if you turn out positive, chances are really good with a highly specific test that you have this problem. Okay, what we're going to do during class time is working on the assignments. We're actually going to calculate sensitivity and specificity for a couple of different tests, and I hope that things will be clearer when we do that. Another way you can use sensitivity and specificity information is to draw out something called a receiver operator characteristic curve. And such a curve is shown here on the right-hand side of the slide. With this curve, what you do is you take a test, and in this particular case, they use the timed up and go test. Okay, so they're looking at the sensitivity, the number of true positives plotted on the y-axis, versus 1 minus the specificity, which would give you the number of false positives on the x-axis. And when they do this at a number of different cutoff times, they found that using a cutoff time of 12 seconds, which is the first box there, gives a sensitivity of 80% and a specificity of 0.87. You can think of sensitivity as 80% and specificity as 87%. Now, this is a pretty good specificity here, but the timed up and go test is really a good test for screening individuals. It's pretty fast. I know you haven't learned it yet, but we'll talk about it and you'll hear about it in CP3. Timed up and go is a really good screening test. It doesn't take very long, minimal equipment. So it's really good for screening for somebody who might have a fall. Okay, if you're just screening for somebody who might have a fall, as opposed to having a higher specificity, you might want to choose a cutoff time that gives you a higher sensitivity. Because remember, a highly sensitive test won't miss a true positive. And in this case, you want to identify fallers, right? So the difference between an 80% test score and an 87% test score, I'd rather go with the 87% test score. That gives me a better feeling that I really know what I'm doing, and I'm going to be able to identify people who have a high risk of falls if I use a cutoff time of 11 seconds for this timed up and go. And that's essentially what you use the receiver operator characteristics curve for. Individuals who develop special tests determine the sensitivity and specificity of the tests, and then they generate cutoff scores for the outcome measures. They really want to find the numbers that give the highest combination of sensitivity and specificity. But in the case of like a timed up and go test, you really want to identify those who have a possibility of falling. So you'd want to go with a higher sensitivity and it's a good screening test. But if you want to be able to say that this person does not have the disease, and if it's positive, then you're able to say, yes, this person really does have the problem, because a highly specific test is designed to not miss a true negative. So if the person's positive on the test, then he has the problem. Okay, another way you can use sensitivity and specificity of a test, and this is something we won't calculate, but I do know that Dr. Grandio is very big on likelihood ratios, so this is something you will do in orthopedics, or have to understand in orthopedics next year. You can use sensitivity and specificity to calculate this, but it talks about your odds of actually having the problem. So if you have a likelihood ratio that's greater than 10, looking at the chart on the right-hand side of the slide, this is really strong evidence to rule in the disease or the problem. Okay, but if you have a likelihood ratio that is less than 0.1, that's strong evidence to rule out the disease. It's really just changing your odds of having or not having the disease. And another way to look at it is to consider positive likelihood ratios and negative likelihood ratios. And again, these are calculated differently. But if you're looking at a positive likelihood ratio, it's the likelihood or the odds of having the problem with a positive test result, having the disorder, compared to a person that did not have the disorder of interest but had a positive test. Again, all derived from sensitivity and specificity of the test, but it really just shifts your odds in favor of having the condition. And if you look at the chart on the bottom of the slide, you can see that a likelihood ratio of 1 really means that your odds of having the condition haven't changed at all. And the lower your likelihood ratio, so likelihood ratio of 2 increases your odds by 15-fold. A likelihood ratio of 10, the higher the likelihood ratio, you're pretty darn sure that this person has this problem if they have this test that's positive. Thinking about it from the other way, there's something called a negative likelihood ratio. And this is a likelihood ratio that a negative test was found in a person with the disorder versus in a person without the disorder of interest. Like all likelihood ratios, the closer the number is to 1, the less likely that the odds of having or not having the condition have changed. So if you look at the table on the bottom of the slide, you can see 1 is a 0 change in probability, all the way up to 0.1. Okay, if you have a negative likelihood ratio of 0.1, your odds of having or your odds of not having the condition are going to be decreased by 45%. Okay, so that's actually a good thing. So a person with a very low negative likelihood ratio is less likely to have the condition that they're being tested for.